So this is not the dtrace dtrace 101 class or something like that. So you gotta do your googling and reading yourself about how it works. But you see, basically what I'm doing, I'm attaching to an Oracle process, and I'm basically measuring or tracing when some specific functions are called, right? So Oracle is just a big C program, right? So you never should forget it when you do troubleshooting, for example, or optimization. You know, when Oracle is too slow, it must be it's doing something for too long, or it's doing too many times of some operations and so on. So anyway, so whenever a fetch command comes in, then Oracle calls OPI fetch, right? And whenever you actually fetch rows from an execution plan line, then there are different functions called QER fetch ones. This QER means query execution row source or something like that. Okay. So and that's pretty much it. And also I'm tracing logical IOs as well, or not all logical IOs, but only the consistent gets. KCBs, kernel cache buffers, and get consistent reads. So this allows me to kind of see which blocks are read when and so on. This actually was very useful when I once looked into how index skip scans worked. You know, that where do we start from, and then we always have to skip scans always have to go to the first leaf block of the index, and they jump onwards from there. So, but again, that's a separate topic. All right. So before let me just exit this. Actually, I don't need to. Okay, so I'll just show you, you know, what it just displays to me. So if I choose select star from T, you see output like this. Okay, SQL trace is enabled. Let me just now exit and start a new fresh session. It was too much. Okay. I will show you how I measure these things, and then I will show you this couple of slides which hopefully help you illustrate what I'm talking about. So I'm gonna set the array size. It's 500 by default, so I'm just gonna try to keep it simple. So right now I should be able to fetch everything in the in the second fetch. Okay, so this script, I'm just measuring the simplest thing. So this just right now it shows that we are entering a fetch operation, and now we are trying to fetch from a table. Okay, so how do I know that there are some metalink nodes still available in the wild which have these function descriptions, and I have actually written, if you search for a tool called OS explain, again it's in my blog, then it's a simple script which just replaces these function names, what it knows, with more human readable ones. Okay, so did I do sorry, I don't want the OS explain, sorry. Oops. Sed -f OS explain sed. Okay, so basically this just replaces the function QERTB, means table fetch, so it just replaces it with a bit more human readable string, right? So when I look into the execution plan, let me see how should I do it. I'll just hit Ctrl+C. Oops. So when I look into the execution plan, you see there is a plan line number 1, operation number 1 is table access full, right? And my trace actually traces out which execution plan operation we are currently executing. Okay, so So this is this is how we can measure things, right? So, and I will get back to this. Okay, I will show you one more thing what I want to illustrate. So before I go on, you see this is a very simple plan, right? So let's make it a bit more complex. Let's query P. It's just a two-table join of the same table, and I will say where A user ID equals B user ID. All right, and count star from. Okay, so it's just a simple two-table join. I'm not even sure how Oracle joins them, right? We don't know that, so it's up to the optimizer right now. Okay, and I have to hit Control C, so it would. Oh, actually, I can do Control. Nope. I'll scroll to the beginning. So, okay. So what I want to show you here is now this was a more complex plan. So these function calls, what we see, they will go deeper. Okay. And actually, maybe I should make this. Let's see. Oops. No, it's too colorful, so I will just remove that. I'll just use op equals. Okay, so basically now the plan is deeper, right? So it only had one level, but now it has, this is the level 0, this is the first level. If I highlight it like that, that's the second level of depth. That's the third level of depth, right? So so therefore, when you trace a plan like this, you will actually see things like this going on, right? You see, let me just go to the beginning. Okay, if you go to the beginning, this is probably, you see, yeah, so this is table access. Okay, we see index range scans as well, but this is because of the recursive queries which kicked in. So let me just trace once more. So this script is not smart enough to ignore all the recursive stuff what's going on. All right. Okay, now it's better, actually much better. So this query, all the other stuff, with the index range scans, these were some data dictionary queries which were also traced. Okay, so this table is actually a very small one, right? But you see what has happened here. So this is the timeline, or this is the function called flow. We have the fetch operation, okay, and now this has called another function called QER-GS something. So it's a group by sort fetch. This is the operation number 1, right? It's this guy. But you see, this function number 1 only knows how do you group by, or how do you aggregate, or how do you min and max and stuff like that. That's why it's called like sort, probably, or that's why the sort module is used for counting and min and max as well, because part of sorting will be checking whether a value is bigger or smaller than some other. But anyway, the select statement calls the sort aggregate, but the sort aggregate does not have any rows of its own, right? The sort aggregate operation cannot go to disk and read stuff. There are different functions for that, right? So the sort aggregate actually just calls whatever is the first function under it in this hierarchy. So the first function under it is a hash join, right? And you see it from here as well. That's what this dtrace, function called tracing shows you. The group by sort operation now calls hash join. Hash join itself does not have any rows. Hash join only knows how to join rows given to it by other row sources. So therefore, the hash join will call its first child. Whoever is the first row, execution plan line under this hash join in this hierarchy, it will call this number 3. So, and now this will do a full table scan, and as this is a very small table, you see we do one logical IO, second and third, right? So you see, we read this block, we read this block again. So this is two reads on the segment header, and this is now the read on the actual first data block. And as the table is so tiny, one block of data only, then it reaches the end of the data, and that's it. By the way, you can map these numbers which show up here to this table called, there's a table called $KCBWH, which means kernel cache buffer. Why did I do this I/O or logical I/O? So let me just go through all the numbers. So I'm looking for the hex number, so because the output is in hex. So we first went and read the segment header block because I guess we want to count how many blocks up to the high water mark we have, or how many extents, and or something like that. So so this is kernel transaction extent management, initialize something perhaps, and so on. And then we go and revisit the segment header again, I guess, to get some first extents and their locations, right? And there is some optimization that Oracle only picks 10 extents information at a time if they haven't changed it. And when it has scanned through 10 extents, then it goes back to the segment header or the ASS or the space management, or the extent management block, extent map block, and gets more information about the next 10 extents and where they are. And then this is in hex 366. This is just a wrong one, but then we actually proceed to fetch data from the table block, the actual rows. So this is a kernel data scan table fetch. Okay, but that's not what I wanted to show. What's the most important is the hierarchy here. Okay. And usually when I kind of look into execution plans, I kind of use, if I look into execution plans, then I use my mouse quite a lot just to understand the hierarchy here. And of course here we have more stuff going on, not like the execution plan here shows, but there are more levels of depth. But I can just, if I want to see, if I highlight the whole hash join operation, you see the hash join is entered here and the hash join finishes here, and inside this hash join Oracle has now gone to this table first, right? It has gone to this table at line number 3 first, which is this guy, and it actually has scanned through it all the way to the end, and then it has started scanning through the other table. So, and once it has done with this hash join, it actually has sent some rows back. But this group by sort actually just does a count star. So I just wanted to illustrate the hierarchy. So I'm going to show you a slide, and then I will get back to this topic. I will show you what happens when you do a nested loop, and what happens when you have perhaps a third join or some operation in it. Okay. Let's see, how do I make it smaller? All right. So again, this doesn't aim to be the complete explanation of everything what happens in Oracle. So I just want to kind of show you some key points about SQL plan execution. So this is a simplistic example of what happens when you do a join, right? And it's sort of what I just ran on in this other windows. So if you have a 2-table join, right, then basically you will have a function, that's the fetch function, and then you have the join function, and the join function then will go into the whatever is the first table under it. In this hierarchy with the lowest ID, it will go in that. It will fetch some rows, and then it will when it gets some rows, I'm going to talk about what the sum means. Then it can go to the other row source. Okay, but and I'm not going to go into more details at the moment. So there is more about hash join, how it actually does work. But you may actually ask that now you may have this logical question that, okay, what if I have a 3-table join? Okay, so would we have one more table next to these guys? And the answer is no. When you have a 3-table join or multi-table join with 4, 5, 10, 50 tables, then it's not like, so basically the execution plan 3 must grow then, and it will grow higher. So it's not like we would have all these 10 tables next to this hash join and the hash join would somehow join all of them together at the same time. It's not like this. If I have a 3-table join, then I will have 2 join operations. So whatever the optimizer picks now, whatever is the order that the optimizer picks, in this case it has picked the departments table first, right? And whatever optimizer picks as first, this is where we will go in the execution plan, and we will fetch some rows. And now, as nested loop join works a little bit differently than, well, quite a lot differently than a hash join, then the moment we get the first row here, we can immediately go into this locations table. We don't have to fetch all the rows somehow in order to go to here to find matches. Nested loop join is sort of, I guess, flexible enough that it can take a single row, and whatever row comes from here, perhaps from some index or whatever, it can take the single row and immediately go and look for a matching row in this table. Okay. So, but anyway, so the main thing what I wanted to show is that if you have a multi-table join, then that the execution plan 3 grows higher, right? And you can read these things here that only 2 row sources can be joined together at a time, right? So we can only join 2 tables here in the nested loop and only 2 row sources in this hash join, right? Basically, we'll take the results of this first join, and now we will, go to the third table to join the third table to the result of the first 2 tables. Okay. And we could say that the row sources, these are C functions like you saw. These will pass their data up the execution plan 3, and the upper layers can then do something with this data. Okay, and I will show that. So I went a few slides onwards. So this is like an example of a subset of this execution plan, right? If you have many tables, then the execution plan 3 gets just deeper and deeper, right? And you see, we join 2 tables here, we add a third table here, we add a fourth table here, fifth table, and and actually we started from here. Okay, so if I scroll back now one slide, there are again some special exceptions where I won't go right now, but usually it's that the first data access, the first logical I/O happens here. So basically, when you start walking from the execution plan, you walk to the first child without you go to the first child of this execution plan, or basically not first child, the first row in the execution plan without children, right? So basically it's sort of clear. So it is a child, but it's not the parent to anybody else. So this is where the execution starts from, right? So we go all the way. This guy, it doesn't have any rows of its own. It has to fetch them from its child. And this guy doesn't have any of its own rows, and so on and on. They will delegate the work here until we invoke this function. And this guy doesn't have anybody to delegate this work to. Therefore, it has to go and do some logical IOs or physical IOs to actually get some data. And then it returns the data back to its parent, who is the hash join, right? And when hash join is happy with the data, has enough of it, in fact, hash join always fetches all the rows from this row source, which are returned to it. Then the hash join will go to its next child. So basically, so how we join 2 tables is this: that the first child returns the rows back to the hash join operation, and then the hash join can start fetching rows from the other child. Okay, so you may have many questions that are unanswered here, but I'm trying to illustrate the hierarchy. Before all the little interesting details, the hierarchy is the most important thing to understand, or most fundamental thing, I would say. So in that light, when we fetch more rows from this table, it's not like this hash join here somehow goes directly to this table and fetch rows. It would end up in a big mess. There is a strong hierarchy in the execution plans. So this hash join can only go and invoke this function with this table scan on this table, or this nested loop on this table. And this nested loop can choose to go deeper now to fetch rows from its child, but not anybody else. It can only access either this child or the other child. And they will do whatever is needed to produce some rows for the parent. And if they reach the end of data, right, they will just say that, hey, end of data, no more rows. So then this parent operation knows that I don't have to go back there anymore. And basically, they start sending this end of data condition back upwards to our fetch operation. So I'm going to add a third operation here now, just to illustrate what I was talking about. And I'm going to keep using hash joins on this small table right now because it's a very simple example. And let's say where B username equals C username. Again, it probably will come up with a bunch of hash joins. Okay, so I will just show the execution plan first, and then I will rerun the query to avoid all the hard parsing recursive overhead. Okay, so please ignore the first line. So this is the previous fetch finishing. It actually finished earlier, but as I pipe the output into my script, then the Unix pipe buffering doesn't always, sometimes pretty much buffer some rows, some bytes. But anyway, so we gotta read from here. Okay, so you see, now we have 3 levels here, or we have three joins. And as I said, a join only can join 2 tables, right? In this case, in the deepest level, we will join this table and that table, and then we will send the results back to the parent, in number 2, right? And this parent then can go into number 6, into its other child. So first this hash join at number 2 will fetch all the rows what it can get from its child number 3 here, which in turn delegates the work to its children to get the data. And once it sends back all the data from the driving row source, so to speak, then this hash join at number 2 can go into its other child. So you may have a different method for analyzing plans, but when I look into real life plans which are big, then I often use whatever editor or terminal I can to kind of highlight, to do rectangular highlights, highlightation, I guess, of this hierarchical data. But anyway, so let's see whether what I said actually is correct. So basically, from that slide, you might remember that the first data access happens in the first line without children, right? So this again, there are some exceptions when you have some filter operations but I'm not going to do that right now. So the fetch operation invokes the sort operation, or the count star, who then invokes the hash join. So it's 1 to 3. So you see, we went to the fetch, then we invoked the hash join. This hash join went 1 level deeper to the operation number 3, right? But so far we don't see any logical reads, because hash join or some count star operation, they only know how to do their thing, join rows or count rows. They don't know how to do logical reads and walk indexes and stuff like that. They don't know how to talk to the data layer. But anyway, and now we go to the operation number 4, which is the first child without, it's the first line in the execution plan without children, because the number 5 here is not a child; it's a sibling. It's like a sister or brother. So it's fairly easy, to use your eyes to see who has children and who doesn't. Okay, so basically this is where the first operation started. So this is where the first I/O started. So I'm a bit tired. It's a bit late here, so my brain is kind of not functioning as fast as it should. So anyway, so this is where the first I/O started. I'm gonna talk about the buffering very, very soon, so you may have questions. But that hash joins work the way it's well documented that it always fetches all the rows what come from its first child. If a join joins, let's say, table A and table B, if this is now A here, it always takes all the rows what it can fetch from table A before proceeding to table B. Okay. So if the table has 1,000,000 rows, but there is also a where condition where where customer ID equals this, then of course this filtering is done first. And whatever rows pass this filtering, they are all fetched into this table. They are buffered in UGA, or your work area in hash area, or temp if it doesn't fit. And once hash join has all the rows it wants from the table A, or the first one, then it will scan through the second table once, and compare the rows it finds to the hash table what it built in its memory. Again, there are so many more details about hash joins, but this is not the topic of my session here. I want to illustrate the hierarchy and how the data flows. Okay, so and you see what happens then, right? So we are at the deepest level. So let's see, let's highlight this, right? So we went to this table T at line number 4. This guy. We scanned through it. We pulled the data in memory, and now we continue. I mean, this scanning of table 4 is over, and now we will do another scan on the table in number 5. So that's the table B, so to speak, or the second table. And now when we send rows back to the hash join, right? So these children, I mean, the second child starts sending rows back to the hash join. It already has fetched the first child. And now hash join starts sending rows back to its parent. So this hash join here starts sending rows back to its parent. Number 3 sends rows back to number 2. Okay. So basically, this is the everything under number 3 or lower, right? Or everything under. So number 3 is a hash join. This rectangle here represents this hash join and its children. So this is the work. And now when number 3 has sent rows to its parent and sent all of them, then its parent will start accessing the next child under it. So this number 2 can only talk to number 3 or number 6 directly, right? So that's why now it goes to number 6, and usually the optimizer, I mean, should put it that way, should come up with a join order so that the table with the largest number of rows coming from it should be scanned last. In the sense that we don't want to cache a terabyte of data in PGA. We would rather want to cache 100 megs in the work areas, and then scan through this terabyte of data, comparing all the rows as we see them to this in-memory hash table up here. Okay. So again, I'm sure there are many open kind of questions right now, but I will go on with the demo, and then I will take the questions. So you might wonder that, what I said is that hash join always takes all the rows what it can get from its first row source. This doesn't mean that it takes all the rows of that table, because there may be extra where columns, in filter columns, right? Well, not in my case, right? But in real life there will be. So and you might think that, what if there is million rows? Where do we keep it? Well, it's the PGA, right? But and another question is that, do we always fetch all the rows somehow and then only pass them to this the other operation in the execution plan? And to answer that question, I'm going to show you a thing called I'm going to show you how rows cascade through execution plans. Okay, so let's do let's see which. So I'm going to force I'm going to go back to this two table join, and I'm going to hint it. I will say that not ordered. Leading is the modern way of saying this. So I will say that the leading table in the join orders is table A, right? Start from A, so I only have A and B, so we will start accessing from the table A. And I will say use NL. By the way, use a nested loop when accessing the table B. Okay, so when we have rows from table A, and now we want to join B to it, this is the correct way to hint it. I don't need to use this A and B. I can just say this, because this hint really means that the second table, what I'm joining after I've gotten rows from the first child, what join method should I use? Okay, so let me just, I think it will hard parse again. So I will just show you the execution plan first. So this is the execution plan, and I will just run it once more without the hard parse overhead. Not sure whether you saw how much I scrolled, but there is much more output now, because I have forced a nested loop. Okay, and nested loop operations, how they work is basically they don't work in a buffered way like a hash join, but basically, as I said, when they take a first row, when they take a row from the first table, well, we can actually follow this. You see, 1, 2, 3. So we went to 1, 2, 3. Well, we went to 1, 2, 3 here. So we immediately did the first logical I/O in the first table. Okay, and this I/O has completed. We have done 3 logical I/Os because of the again, we did do the full table scan, and we opened the segment header. So and now we go to the operation number 4, right? So basically, we have gone to this operation number 4. We have done some logical I/Os, and then we have gone back to number 3. Because how nested loop works, it takes a row from here, and then it searches for matching rows from this table. And then it goes and picks the same nested loop again, continues reading the first table, and takes the next row from there. And then it searches for matching rows. And then it takes the next row again and searches for matching rows, and so on. That's why the name is called loops, nested loops. So I'm going to change something, one more thing. Instead of count star, I will use select star. Because you see, there is one more field that whenever we fetch from a row source, Oracle says there is a parameter called that how many rows do I want? And this is directly dependent on the array size. But if you use a count star up here, I mean, count star will kind of group all the rows anyway. Even if you count 1,000,000 rows, you will send back only one, right? So whenever you have these count stars or this kind of grouping or ordering operations, which kind of have to fetch all the data anyway before anything is sent back to the user, then it will ask for the maximum number of rows at a time. So if there are more rows, if this particular operation, if there are more rows in this whole table or in this join, then we will just enter this function multiple times. We run it multiple times. So anyway, so that's why I do this. I will use a select star because now I'm not counting it. Now I'm going to send the rows back directly to the user. So I'm just gonna rerun this without the hard parsing chunk in the beginning. So this is the plan. So you see, this is where my select started from. We first fetched one row only, right? I mean, and you see, this is not the fetch from as what the user says. I mean, somewhere here, the SQL plus sent the command that fetch me one row, right? And therefore, when we called the nested loop function, we knew that we only want one row. There is no point in doing more work than the application wants. So this is passed into the all the row sources in the execution plan that we only want one row. So we know when to quit, right? So and this passes it into this fetch operation as well. This is operation number 2. So that's the table scan full. So we have to open the segment header blocks twice and this table block itself to get a row, and then we return it back to this nested loop. So we have one row from the first child here, and now the nested loop goes to the other child to get one row from that to see whether it matches, and we get the row back. And as we only requested for one row, you see this is now where the fetch finishes. So we would actually see all the SQLnet message waits and so on in here. So we have been able to finish, send the data back to the client with only doing that small amount of work. And now the next fetch comes in, and as the array size is 500 in my SQL plus, now we have to continue looping as long as it takes until we have 500 rows or until we run out of data. So again, operation number 1, this is the nested loop, so which jumps, you see what happens here. So then the new fetch came in, and now this nested loop jumps to operation number 3 right away. It jumps to this row source. This is because it probably was smart and it probably fetched a bit more rows in sort of like some internal pre-fetching way into the UGA. So that it would not have to kind of go back to this row table right away. Or actually, you know what this is? Because, I mean, if I take a row with value number 5, and now I search for number 5s from here, well, if I find one, I could send it back right away. But now if I fetch more, maybe there are more number 5s, right? That's why Oracle continued scanning this. But again, when the query execution started, it definitely started from this, as I said, right? I'm not sure how much this makes sense at the moment, but you see, as so we go to this row number 3. We fetch some data, and let's see whether it. And we did not find a match apparently, because next time, you see, now there is the next iteration under this nested loop. There is a next iteration, operation number 2. We take the next row from here, and we go to this operation number 3 again. So we take the next row from number 2, and then we start looking for matching rows in 3. And somewhere, when we loop and loop and loop through this this table, and it's actually interesting why why the number 2 doesn't show up here. It must that's actually interesting. Yeah, I don't want to go any deeper, but so this is actually, I was expecting to see number 2 to show up more, because so basically one thing what I wanted to show you is that this parameter kind of it decreases because we keep finding rows which match our okay, now I actually get it, because this is nested loop. So when we have like 36 rows in this table, right? When we take the next row from this table, then Oracle will call. Basically, it has to scan through this table as well, and for every row it finds, it will immediately feed it back to the parent, because maybe there is another nested loop or something. Maybe we want to send it back already. So that's why I think we will see like 36 of these operations. Each of them return one row, and they will be called again, saying that okay, now we need that many rows. We need less rows because our array size is kind of getting fuller and fuller. Okay, and as we reached the end of data condition before the array was full, then we returned, like 33 rows or 34 rows back to the client. So I wanted to show you how the looping works. You see, I already feel that I think it's not structured enough and detailed enough, because it's just a hacking session. But I wanted to show you that the difference between a hash join and the nested loop. So hash join will sort of fetch all the rows from its first row source first, and then it buffers them, and it never has to go back to the first table, on disk, and then it scans through the second table only once. But nested loop will loop through it, and in my case, it's like a bad situation because you see, I don't even have an index on this inner table. So I will create an index quickly. So I will say create index I on T, where, not where, and I think it's the user ID column. Okay. I'm using you see, I'm using 3 types of hints: the join order, join method, and access paths. So this is how you this is almost everything that's needed to completely tie down an execution plan. But again, in real life, there are more things like hash input swapping and so on, which may cause trouble. So let me just run it once more without the overhead. And there is one more weird thing, so which shows not weird, but I have a 2-table join, but Oracle actually has added one more layer of joins. So it actually accesses the table of the table B this way. That it first joins the table A together with the index on the table B, and kind of can do some filtering there. The join will filter out some rows, and then whatever rows survive this join, it takes these row IDs and fetches the table the blocks from the table. So this avoids fetching too many blocks just to see that, hey, the rows what we want are not in there. So now this join went even deeper. So I think it's already a bit too late for my brain, and I kind of want to save some time for the questions as well. But you see, okay. So this is So I hope I managed to show a little bit of about the hierarchy here, and and I will upload the script as well, so you will you can run experiments yourself. So no need to guess, right? And and you never will see something like this nested loop going to its grandchildren and pulling data from there and so on. So so it's and why I'm spending time on this hierarchy is that as long as you understand the hierarchy and follow that, it doesn't really matter how big the execution plan is. I mean, it does not. I mean, small execution plan with 5 rows has exactly the same rules and hierarchy as a big execution plan with 500 rows in it or 500 lines in it, right? So that's why it pays off to kind of understand the hierarchy, how the data flows. Okay, so I will not do dtrace anymore. It's I think already deep enough, but I will just show you a little bit of when you use the gather blend statistics. So basically, I used dtrace in hope of showing like hard evidence how some execution plan steps are actually executed, right? But what we can do in real life in everyday troubleshooting and optimization cases is just use Oracle's metrics, either SQL monitoring reports or the SQL basic SQL performance profiling, really, or plan statistics gathering. And so basically, I run this query like this. There are some parameters I can use if I don't want to use the hint, but what this gives me is starts. Okay, so what you saw in dtrace, it's actually one level deeper. So you saw all these fetch functions. So this is actually even one level deeper than the starts. But I'll just illustrate this first. So you see, this is the key, or this column and the actual rows column. These are a really important. These are very important for understanding why some SQL plans are slow, even though you are using your indexes and so on. And basically, as I said a bit earlier, when something is too slow, let's say your query is too slow, it's really only two reasons. Only two reasons why is it slow. Either it's doing too many operations, or these operations take too much time. In other words, when we talk about I/O, either if your query waits a long time on I/O in total, well, it's either that your I/O is slow, your storage array, responds very slowly, or you are doing too many I/Os. And you can extend the same logic elsewhere as well. If your query is using too much CPU, right? It's maybe doing some index range scan. Maybe it's doing a single index range scan which does billions of logical reads because it's so wide index and you scan it from end to end for some reason. So maybe this index range scan is so slow, so time consuming, or maybe the index range scan itself is fast, but you're just doing it so many times. And this is why the starts comes into play. I mean, this actually tells you how many times I started doing an index range scan. So so if you wonder about the relationship between the starts and the fetches you saw in dtrace, well, if you start a range scan, it means that you're searching for a new range of values. And within that search of new range of values, you might fetch one time or 10 or 10,000 times, depending on your array size. Because maybe the index range scan will return you 50,000 rows, right? So if your array size is 500, then you have to continue that index range scan, 99 times or 100 times, right? So the starts tells you how many times we started looking for a new range of values. And now you might wonder, how come when I execute this query, I executed this query once, right? Because you see, the select statement itself, it shows that it's executed once, right? Why do I do 34 index range scans here? And the answer here is, this is how nested loops work. Nested loops go, for every row, every actual row, you see, for every row that the nested loop gets from its first child, it will go and visit its second child. Unlike hash joins, hash joins are different. They only go through. Well, actually, I don't have to talk about it. I can illustrate it. I will say use hash. You see, this is well, now the plan is slightly different because the nested loop extra join what Oracle caused is gone. But you see, the starts is 1. So hash join scans through this data. It will buffer the results of the first table. These columns which you need, and these rows what survive some filter condition. It will buffer them here in this hash join area, and then it will go and start fetching. It fetches all the rows from the other table. And while doing that, so dtrace would be good to illustrate this, but I think it's too much for now. So hash join, it does not have to buffer the second row source. Yes, it has to buffer the first row source, but it doesn't have to buffer your terabyte fact table in memory somehow. It actually kind of just sort of trickle feeds the data. As it goes on reading, it will send an array full of rows back to the hash join, who can immediately do the joining and comparison and send the matching rows back to its parent. And this parent finally sends the rows back to the application. But from here you see that the hash join was only did this index range scan once. This is an index range scan from, it's a full index range scan. It's from end to end of the leaves. Why does Oracle do that? Well, it's just because I force it to use an index. But you see, the starts column is one takeaway if you haven't used it before. It illustrates you, it tells you how many times you did something. Okay, you see, this is the nested loop case. In nested loop we did 34 index range scans because our parent, who is this nested loop, got 34 rows from the first child, right? So if this first child had returned 1,000,000 rows, then the nested loop would have had to go here 1,000,000 times, perform 1,000,000 range scans. That's how nested loops can be very CPU consuming and slow, even if they use all the indexes they can, right? So the execution plan efficiency doesn't only depend on which index you use. It depends on 3 main things: join order, join method, and which index you use, access path, right? And obviously what order and method and path is the best, it depends a lot on how many rows will be returned from different tables, right? Okay, so my dtrace demo here hopefully helped a bit to illustrate where do these numbers come from and what really happens internally. Okay, so I think it's time for questions. I'm sure there are a lot of them. Before that, I'm just gonna show you one somewhat related thing. I mean, if you don't know SQL monitoring reports yet, then you should research them. If you have the diagnostics pack licenses, of course, and tuning pack as well, they allow you to look inside an existing running SQL plan and see how much time was spent on each line, right? something like this, but I had to explicitly enable it, and it's, I cannot enable or should not enable it system-wide because it makes everything consume more CPU. But it is possible to get execution plan line level information even without these extra licenses, right? But what I want to show you is one script. So this is just running my snapper, which tells me, some lists me which SQL IDs are the most active. So that's not what I want to show. Look into the snapper session if you want to see that. What I want to show you is this. So this is an OLTP system. It's the swing bench benchmark, which does OLTP like workload, and I cannot really monitor. I cannot really use SQL monitoring here. I mean, I could add, if I can change the code, I could add this monitor hint for every single query to get it monitored right away. But this is a bad idea in OLTP, because SQL monitoring is meant for monitoring long-running queries, not the ones which are executed 1,000 times or more per second. You would end up with a huge CPU overhead and also some SQL monitoring area latch contention when you do that. So that's why I wrote my script called Ash-based SQL monitoring. It's a basic script actually. It just does a group by from Ash, just like Ash. Or actually, it doesn't. I think it does a group by. Yes, it does. But just like you should, right? Should use Ash data. And I will look into child number 1 because apparently child number 0 has been executed only a few times, and let's see. Anyway, so I'll take the more heavier one. Okay, so SQL monitoring does not work on OLTP queries because it does not, when you have queries which run really fast, like less than a second per execution and so on. SQL monitoring only kicks in when your query runs for 5 seconds, or basically when it uses CPU and I/O wait time more than 5 seconds. But this is basically an Ash-based query. It just it uses the new fields in Ash. I've shown these in many places. So starting from 11G, you don't have to satisfy with the top SQL from Ash. You can actually drill down into an execution plan line level and group by that, right? And that's what my script does here. So, and it's actually very wide. I'm gonna show you because I use it in real life. So execution plans tend to be wide. So SQL monitoring doesn't monitor short queries. However, if these short queries run for long enough, for many times enough, like in busy OLTP systems you have, then from Ash we still can aggregate this information together. That which step in this execution plan took the most time. Okay, so basically, and if you look into this, this is the execution plan line ID. And you see it's line number 2. How come we have 3 of these? It's because I have the wait events here as well. I just do a further breakdown by the wait event. So basically, just like SQL monitoring report gives you automatically for long-running queries, you can get the similar info from Ash as well. And if you wonder that in which line some OLTP query it's spending most of its time, and you see this seems to be some simple enough query. It's not, there's even no join here. I should look into some other table later. But from here I immediately see that, hey, most of the time is spent here. So if I want to fix anything about this query, then I should first look into why does this table access by row ID take so much time. It's waiting for sequential reads so much, occasionally even scattered reads. Okay, Well, as this table is accessed using the row IDs, which are fed to it by the index scan under it, right? Because this is the child. This is the index scan, right? So I mean, and then it looks like 39% of time is spent doing sequential reads on this index, right? So this is actually not a very good example because it's not, there are no joins here or anything, right? Like that, right? Because there is nothing much you can fix for so simple query. Well, because it already is doing a unique index lookup, right? But the only thing perhaps is that maybe we can avoid going to this table if we added some columns into this index. So it's a so trivial SQL, so there is not much you can do. So you see what I do here. I highlight all of this. Let me actually do this. I will highlight all the rows related to this table. So, and all the bottom ones are about this index. So I can just go scroll right even more. So this might look better in SQL monitoring output, but that's why I highlight things. You see, I actually put the predicate section right into, I don't put it under the plan, but I put it onto the same line with the execution plan lines themselves. Because if the plan is like 200 or 500 lines long, then scrolling back and forth will be pretty hard. It's much easier for me, at least, to highlight some rows and scroll left and right, because from here I would immediately see what predicates we had on this index. Okay, so or on in this query, right? So this query only used a single predicate. So so this index, whatever would be the optimal index, would only, I mean, would have to pretty much start from this with this column. And the projection is a really cool field which is not used much. Projection tells you what columns were sent upwards to the parent from this particular line. So these lines in the bottom, these are the index. This is the index access. So we are sending the customer ID back up to the parent operation, and we are also sending the row ID, which we got from the index. I mean, we need the row ID because we need to know into which block should we go to read the table part of the row, right? So, and when I scroll right, so the highlighted part is these columns were the ones which were returned from that select part now, or sorry, from the table access part. And in this case, you see, we take quite a lot of columns, so we're not going to put all of them into this primary key index likely. But sometimes one quick way you see that could I avoid going to this table is this, that if the only extra column, in addition to the index ones, is the customer first name, for example, then there is a case, to make this simple query faster, I might want to just add this column into the index, and I never have to go to the table. And that would save quite a few, quite a lot of the time that way. I'm gonna pick one more query, which is a bit hopefully more complex. And then I will take questions, so it's a promise. Okay, so this is insert, so that's even worse. So I think I'm not going to spend much more time, so because I plan to write the blog entry about this anyway. So basically, with Ash data on 11G, you still need the diagnostic spec license to query Ash, right? But with Ash data on 11G, you can do sort of SQL monitoring like analysis on OLTP queries as well, which run too quickly to be monitored, right? And you want to do it because you want to know in which execution plan line most of the time is spent. Wow, there are so many questions. So I will. In the bottom there is a question that where do you get the recording? So I will answer it with text. Will be at http Enkitech.tv. I just sent you a reply. So Enkitech.tv is where the recordings will be. So this is the site where the recordings will be. Okay, and if you look through the other videos, there are lots of other videos as well, which explain how full label scans work and things like that. So let's see. I think I'm gonna spend maybe like 10 minutes on questions and answers. So then, and if you're not, and I have to finish then, because there are people who are, I guess, still in the office listening to this. Okay. Okay. So there is someone asked a question about the elapsed time. That why is this elapsed time cumulative in SQL trace output when it prints out the execution plan stats, or here? You see, let me just do this, what I usually use. I just say select, what is it? Select gather plan statistics, count star from DBA source. So I just took something which is a bit bigger, right? And where I actually accidentally got into even a more problematic one. So the actual times here are cumulative, right? However, so basically what it should mean is that whatever, I mean, and actually what it means as well, but I will explain the anomaly here, that whatever times you see here, this view operation, right? It took 2 seconds, right? But it doesn't mean that we spent all these 2 seconds in the view line running some code there. It actually means that the view operation and all of its children, these guys spent 2 seconds. Or if I wonder that, you see, half of this is spent in this filter, but again, it's not only this filter line, but filter and all of its children. This is where the second went. Okay, you see how I just use, I highlight the block and I immediately see where filter's children end, and and next sibling under the common parent starts, right? So these times reported here are cumulative. For the single reason, this is where the dtrace output will be useful. You see, these timings, the actual timings, are calculated this way. When this nested loop join starts, right? When this join starts, Oracle takes a timestamp, right? It checks what is the current time, right? And now when this nested loop operation ends, it checks the time again, and it returns the difference. This is the actual time as far as Oracle sees. So basically I can highlight this. Oh, sorry, it's the wrong one. You see. So Oracle just takes a before and after timestamp. Okay, so this is the actual time spent in the nested loop. And now when we go deeper, somewhere else in the plan, then when Oracle enters this nested loop, it takes timestamp when it enters this nested loop, and when it exits, it takes this. So and it shows that as the actual time for that nested loop line, and so on. When it goes deeper, this table access, and so on. So it does not somehow do the calculation, which is not too hard though. It does not somehow it doesn't do the calculation to exclude the child time. So this cumulative time here includes the time spent in this line itself, plus all the children in the hierarchy, right? And here it's similar. So let me just pick this 14. So this 14 here includes the time spent in this nested loop and all its children. And when you go downwards, you see, I mean, how we can read this is that this child, so this child has used 14, whatever, 0.14 seconds. And I can kind of go down all the way to find, where is the last, big time consumer in this hierarchy. And I see it's this guy. So basically it looks like this full table scan took 0.14 seconds. And as these numbers are cumulative, the parent just includes it in itself as well. If you visualize the dtrace output, that's how it is. Because if a child runs for 2 hours, then the parent must, parent is waiting for the child. It must run at least that much. But it doesn't explain why this happens, and this happens because Oracle starting from 10G, it doesn't measure every single function call separately. It measures the time only every 128th time you enter it, and then it extrapolates the numbers from there. And if you get unlucky, it gets an incorrect estimate. There is a parameter called row source statistics sampling frequency. So in this case, if you see these weird numbers and you cannot use SQL monitoring report, which is more accurate, you can just set this to a smaller number, which means your query now will use even more CPU, because it will query the actual timestamp every time it calls this function in a nested loop, for example. And now we should have a more correct number. So with this parameter, the whole query ran longer because it's just monitoring overhead is bigger. But with this parameter, I told that don't only sample every 128th function call, but actually measure every single function. And now the hierarchy is correct. This was the parameter. Okay, so let's see if we can take one more question. So Jay has asked that can I show an example where the OPI tracing can be used for our advantage? And the example, one example is of course our own learning purposes, but the other example was where I actually have used OPI tracing in real life, was when you have lobe access and things like that in before 11G especially. So whenever you use SQL trace and it doesn't show all the time and you see that hey, something else is going on, then OPI trace may be helpful. So I'm just gonna so Bjorn asked somewhere in back that doesn't full table scan you high water mark, and shouldn't it be more blocks? I guess it was when I scanned a really small table and everything fit into one block, perhaps. But again, even if you scan a big table, let's say with a hash join, and as I said, the hash join will take all the rows which match the filter conditions and so on from the first table. Then if you follow how the functions get called, even the hash join only takes an array full of rows at a time and then puts it into PGA, and then it continues, it goes back to the table scan and continues reading this array full of rows and puts it into PGA and so on. So there's always looping somewhere. I mean, nested loops name says that there is looping, but hash joins and sort merge joins, they all do some sort of looping, because it's not wise to take a gigabyte of data and buffer it and then return it to the top layer or the upper function. It makes sense to break the work into pieces and take an array full, few kilobytes, few hundred kilobytes of worth of rows at a time, and pass this array upwards the execution plan tree, as opposed to taking a gigabyte at a time and then processing it. I'm not sure how much sense I make by now, but if you really want to measure things yourself like that, then you can use dtrace. But of course, I do have a SQL tuning class which is actually structured and then has slides and decent demos and everything, which starts next week, as I said. So a little bit of advertising as well, if you want to really understand and put it into context. Anthony asked that the row source statistics sampling frequency should be a power of 2, right? You see, it should be a power of 2. How come it accepted value not value number 1? Well, if I take power 2 0 from number 2, then it's 1, right? Value number 2 in power of 0 is 1, so that's also a valid value. So let's see. Okay, so I will share again where the session will be. Okay, it will be. Oops, come on, what's going on? Okay, now I cannot type. Okay, the recording will be at http://architect.tv, and I will try to upload it today, but if it doesn't show up today, then tomorrow. But there is plenty of other stuff to view then. Okay. Stefan asked that, about my earlier lob demo, that does Oracle need to get the lob locator and do an extra call, even if the lob is actually physically stored inline? And the answer is yes. That's how lobs work. Even if the lob is so small that it's actually right there with the table inside the row itself, then still when you do a select, then Oracle first returns lob locator, and then the SQL Plus itself has to go and pull the lob contents.